Imagine packing over 1 million people into a dense, ancient urban grid with no modern plumbing. At that scale, a city doesn't just need food and shelter, it needs a way to keep from drowning in its own waste. The Roman solution was a gravity-driven network that delivered hundreds of millions of gallons a day. It was a staggering volume of water that wouldn't be seen again in a major city until the 19th century. To understand how they sustained this impossible density, we're going to track the journey of a single drop of water from a distant mountain spring all the way to the Tiber River. For Rome, managing this continuous flow was the logistical floor. Without this water, the city's population density would have made it biologically uninhabitable within weeks. Our drop begins its journey miles outside the city. The primary challenge for Roman engineers was maintaining a precise, gentle downward slope over dozens of miles of unpredictable terrain. Surveyors used a chorobates, a 20-foot wooden table. Using water troughs and plumb lines, they established a perfect horizontal plane. Because the gradient had to be constant, engineers bored tunnels through solid rock and built massive siphons to cross steep hills. When a valley was too deep for a siphon, they had to carry the water channel across the gap, building massive structures to preserve that critical elevation. Structures like the Pont du Gard used 3 tiers of stone arches to keep the water channel exactly on grade, 160 feet above the river. These weren't built for decoration. They were massive, functional machines designed to harness gravity and manipulate the landscape. When the water finally reaches the city walls, it enters the Castellum Divisorium. This distribution tower splits the massive flow into 3 distinct urban zones. Beneath the streets, our drop enters an intricate network of terracotta and lead pipes. This pressurized system branched out to serve fountains, workshops, and private homes. But did this massive plumbing project come at a cost? A popular myth suggests these lead pipes poisoned the population and triggered the empire's decline. Bioarchaeological evidence says otherwise. Because the spring water was so hard, mineral deposits quickly formed a thick calcified barrier inside the pipes, insulating the water from the lead walls. While Romans were exposed to lead from many sources, the city's plumbing was an effective distribution network, not a biological death sentence. A vast amount of this water eventually flowed into the thermae, or public baths. These were the primary social centers of the city, where citizens met to conduct business and discuss politics. The sheer size of these complexes, like the baths of Caracalla, shows their importance. They were sprawling, high-capacity facilities designed for thousands of people. To maintain this experience, the Romans relied on the hypocast, a subterranean furnace system that allowed them to control the temperature of the water and the air. The hypocast functioned by circulating hot gases from wood fires through a hollow space beneath elevated floors and up through the walls. In the baths, a citizen would move from the changing rooms to the exercise courtyard, eventually alternating between heated pools and cold plunges to finish the routine. This was where the state's massive infrastructure investment became a daily reality. For a nominal fee, any citizen could access a level of hygiene and luxury that would have been impossible without the aqueducts. But as the water leaves the baths, it becomes a vehicle for waste. This now dirty water was diverted to flush the city's public latrines. This creates the great paradox of Roman life. They possessed genius-level macroscopic engineering, but they had no understanding of microscopic germ theory. Because the baths were rarely drained or treated, the sick and healthy bathed together, and the pools often became concentrated reservoirs for infection. In the latrines, users shared the tersorium, a sea sponge on a stick. This shared tool became a primary vector for intestinal parasites and dysentery across the city. Rome's engineers could move millions of gallons of water, but without a concept of bacteria, they inadvertently created communal breeding grounds for disease. The final stage of our drop's journey is a flush into the Cloaca Maxima, the greatest sewer. This massive subterranean channel collected the city's waste and sent it toward the river. The durability of this construction is remarkable. This ancient archway still stands today, functioning as part of modern Rome's drainage. At its height, this system dumped millions of pounds of waste into the Tiber daily, scrubbing the city clean at a macroscopic level. This infrastructure didn't provide perfect public health, but it did provide the technical foundation for a city of this scale to exist without collapsing. Rome's lasting legacy proves that a high-density metropolis is only viable when a society masters the continuous management of its water and its waste.